So this was a question. In between, I had some technical issues with the screen, so I don't think all of you got this particular problem. You could see this now, right? Okay, so one second. Yeah, this was a question. The matrix P, which is given as 0, 0, 1, 1, 0, 0, 0, 1, 0, rotates a vector about the axis 1, 1, 1 by an angle of. So this particular matrix, anybody got the answer for this one? Anybody got the answer for this question? I have kept this question as activity for you. For those who have joined early, you need not sit idle. You can always work out one particular problem I'll be keeping in the screen. Anyone got the answer for this one? No. Formula 120. 120. Formula used. Okay. Formula used is you used the formula 1 plus cos 2 theta equal to 1 plus 2 cos theta equal to 0, right? Yeah. Answer is 120, but we'll see what it means actually. Okay. So this particular question, this matrix is actually a rotation matrix. This matrix is a rotation matrix, which means if you are given any rotation matrix, then the it rotates a vector about an axis. Means it simply means any vector which is perpendicular to this plane. For example, if I consider a vector in this particular direction, there is a plane perpendicular to that vector, correct? For example, this plane, this vector is actually 90° with this plane. Any vector which is perpendicular to the plane. For example, another example is if I consider a three-dimensional plane. This plane, if I consider, this vector is perpendicular to that plane. So any plane which is perpendicular to that vector, any vector which is drawn in that plane will be rotated by this particular matrix. Okay, by how much it will rotate, that is the basic idea. So you can check for any vector. My idea is it will rotate any vector, by an angle of theta, but the vector should be lying in the plane perpendicular to this vector. Okay, perpendicular to this vector. So I assume any vector which is lying in a plane perpendicular to this vector as xi vector plus yj vector plus zk vector. If this vector is perpendicular to this vector, what does the idea we have? If they are perpendicular, I know they are going to be orthogonal, hence the dot product will be 0. So this is 1 I vector plus 1 j vector plus 1 k vector, right? If I dot product these two vectors, my result will be x into 1 plus y into 1 plus z into 1 equal to 0, because dot product has to be 0. So my vector which is assumed to be perpendicular to this vector is xi vector plus yj vector plus zk vector. Now if I operate that particular vector with this matrix, what will be the result? 0, 0, 1, 1, 0, 0, 0, 1, 0. 1 second, please hold on. Please wait. One person did not get our invite who has joined today, so I'll just add him and we'll continue. Wait for 1 minute. Okay. Okay. Sits Vishnu.pk. Sits undo. Sits Vishnu. Sits Vishnu.pk. The right gmail.com. Okay. Done. Right, we will continue with our discussion. So any vector which is perpendicular to this vector, I have assumed it to be xi vector plus yj vector plus zk vector. Since they are perpendicular, their dot product has to be 0. So x plus y plus z will be equal to 0. Right? Now if I operate this particular vector, that particular vector with this matrix, what will be the result? The result is going to be, so you can see 0, 0, 1. So this will be z, 1. So this is x, 0. So this will be y, correct? This is the result. So this is the resulting vector. So any vector, I have given this vector into this matrix. The resultant vector is this one. So actually what they have asked in the question is the angle between these two vectors, right? So my new vector, so my resultant vector, I can write it as Z I vector plus X J vector plus Y K vector, right? And I know the first vector XYZ is going to lie in the plane perpendicular to this axis. That condition has given me another result, which is x plus y plus z equal to 0. Because any vector which is lying perpendicular to this axis will have a dot product with this axis equal to 0. Right. Now I have two vectors. One vector is xyj. So this is our original vector. I'm making it as O. xi plus yj plus zk. Now I have operated this vector with this matrix and I got the resultant vector, this one. What is going to be the angle theta between these two vectors? I can dot product these vectors. You know what is meant by dot product, right? A vector dot b vector equal to a magnitude of a into magnitude of b into cos theta, correct? So if I dot product these two vectors, the result will be h times z plus h times y plus y times z. That will be the dot product r vector dot o vector, correct? R vector dot o vector will be h times z plus h times y plus y times z. Now let us see what can we get the result from that equation, because I know the angle between the vectors can be obtained from dot product. So I'll write what is the magnitude of r. Magnitude of r will be root of z square plus h square plus y square, and magnitude of o will be root of h square plus y square plus z square. So these two terms are same, correct? H square plus y square plus z square here, h square plus y square plus z square here also. So magnitude of first vector into magnitude of second vector into cosine of angle between the two vectors is equal to dot product. What is the dot product? Dot product is this term, correct? So I can write cos theta will be equal to this dot product divided by this term. So that is hz plus hy plus yz whole divided by, these two terms are same. So their product is going to be h square plus y square plus z square, correct? Now I'm going to apply another concept now. See, I'll just multiply numerator and denominator by 2. So 2 times this will be hz plus yz plus hyz, sorry, hz plus hy plus yz. This is one time, plus again I am adding that term hz plus hy plus yz, right, divided by, I have made the numerator 2 times, so denominator should also be 2 times, 2 into h square plus y square plus z square, correct? Now you can see the next step, what I'm going to do is, see, this is a lengthy procedure, so you need not take it down right now. I'll give an easy solution for this later, but you should understand the basic idea of how it is obtained. That is why I'm working out this one. So hz plus hy will be nothing but h into y plus z, correct? Similarly, yz plus hz, sorry, yz plus hz will be nothing but z into h plus y, correct? And the last term hy plus yz will be nothing plus y into h plus z. Okay, so h into y plus z should be, I have the relation h plus y plus z equal to 0, correct? So y plus z will be minus h. So I can write this is equal to h into minus h plus this is equal to z into minus z plus this is equal to y into minus y. So this is minus h square minus y square minus z square. Now the numerator term is, nothing but, numerator term is, what is numerator? Numerator will be, right, numerator will be minus of h square plus y square plus z square, correct? Divided by denominator is 2 into h square plus y square plus z square. So I can cancel out. So my cos theta is actually minus 1 by 2. Cos theta becomes minus 1 by 2 and theta equal to 120 degree. So the answer is actually 120 degree. But this is a complicated procedure. I actually just wanted you to understand this process. You never do try attempting this way. You can actually copy this one. I have gone it a little bit fast. So the lecture will be available as recorded session. You can try that one, observe it, and write it down what has actually happened. But I'll do it in a pretty easy way. We can directly apply a formula to evaluate the angle which it rotates. That particular formula is a specific one for three-dimensional vectors. Okay, three-dimensional vectors, it is specific. So for three-dimensional rotating matrices, for 3 by 3 rotating matrices only. Okay, for 3 by 3 rotating matrices, 1 plus 2 cos theta will be equal to the trace of the matrix. 1 plus 2 cos theta will be equal to trace of the matrix. The proof of this is beyond the scope of our class. So you just can take it down. This is applicable only for 3 by 3 rotational matrices. Okay. For 3 by 3 rotational matrices, for 3 by 3 rotational matrices, 1 plus 2 cos theta will be equal to trace of the matrix. So here the trace of the matrix is 0 plus 0 plus 0. So I have simply 1 plus 2 cos theta equal to 0, which means 2 cos theta equal to minus 1 and cos theta equal to minus 1 by 2. So theta equal to cos inverse of minus 1 by 2, which will be equal to 120 degrees. So this is the easiest way of solving this particular problem. I would prefer you to learn this particular formula because the other procedure is a bit lengthy. I hope this idea is clear. Any doubts? Any doubts? Any doubt for anybody? Okay. Right. 1 second. Is it clear to you? Nobody's responding. Should I clear? Okay. This is enough. Which one? The last one is enough for you. Okay. The first part is little bit complicated. You need not. Yes. Okay. So right now we'll move on to some more questions actually were there. Yeah, in the last class, in our tutorial class, actually we have done one problem, and after the class, a student asked me how we got the answer for this one. So I think it was already given. I mean, the idea was described in the class, and then I memorized that this point was not discussed in the class. So I thought I'll teach this particular concept using this problem. Okay, so hope you remember what was the answer for this one. What is the answer for this one? What was the answer for this particular problem? This particular problem, we got the answer as B. Right? How you got the answer as B? That is important. Right? How you got the answer as B? See, we can directly write the answer as B because you must remember two particular points. One is if you have eigenvalues of A, that will be eigenvalues of A. Eigenvalues of A, that will be same as eigenvalues of A transpose also. Eigenvalues of A transpose also. Now this is not applicable for eigenvectors. Okay, eigenvectors, you must remember this. Eigenvectors of A not equal to eigenvectors of A transpose. Okay. So that's an interesting property, but eigenvalues of A and eigenvalues of A transpose will be same. That means if you know the eigenvalues of this matrix, the eigenvalues of A transpose will also be the same. Yeah, eigenvalues of A transpose will be the same, but eigenvectors will not be the same. Now the next property which you should remember is if you have any column, okay, any column, this is an important property. If any column with only one non-zero element, any column with only one non-zero element, comma, and if that element is in the diagonal element, if that element is a diagonal element, is in the diagonal of the matrix, if is in the diagonal of the matrix, diagonal of the matrix means your row number and column number should be same, diagonal of the matrix, then that value will be an eigenvalue, then that value will be an eigenvalue, then that value will be an eigenvalue. This is an important property. Okay, so now you observe the first column. I have first column given to be 2 0 0 0 0. I know it has got only one non-zero element, which is happened to be which has happened to be in the diagonal of the element. So that value is an eigenvalue. So I know 2 is an eigenvalue, right? Similarly, if I take this particular row, this particular column, 0 0 0 0 4, so only one non-zero element is there, which is again in the diagonal of that matrix. So that value will be an eigenvalue 4, right? Now, since the eigenvalues of A and A transpose are same, the idea which I have mentioned here for column, it will be applicable for row also, right? Will be applicable for row also. So you can change this point as any rows or columns with one non-zero element, with only one non-zero element. And if that element is in the diagonal of the matrix, then the value will be an eigenvalue. Now you can check for row. See, this particular row has got only one non-zero element, and that particular element is in the diagonal of the matrix, right? So I can say 3 is also an eigenvalue. Similarly, this particular row, I have only one non-zero element. That element is in the diagonal. Diagonal means third row, third column. Here, second row, second column. First row, first column. Fourth row, fourth column. So that particular value, which is -2. So I know these four are the eigenvalues of the matrix. Is it clear? Is it clear to all of you now? Because I think someone called me after the class. How you got the answer? So that is about this particular problem. Actually, I have given a video of this particular problem in the YouTube. It will be uploaded today. It is already uploaded. Any questions in this? Shall I move forward? It's clear. Okay. Right. Now, can you quickly answer this one? We will work out some more few questions and then move to the concept. Okay. Yeah. Correct. All of you are giving the answer as one. So product of eigenvalues will be 4 here. Determinant. So product of eigenvalues will be 4 in that particular question. Product of eigenvalues will be 4. So determinant of A will be 4. So determinant of A inverse will be 1/4. Okay. So that is 0.25. I think Manjunath, Ashwati, KR, Sujit, Shekhin, Nathira, Vishnu, Archana, KR, Arvind, all of you got the correct answer. So I'm moving forward. What is the rank of this particular matrix? Can you say what is the rank of this particular matrix? Any answers? Rank is 4. So you have converted it into echelon form and observe that all 4 rows are non-zero rows, correct? Others? Sujit got it correct. So this I have actually explained the procedure before, how to convert a matrix into echelon form. You just need to do the elementary row operations. Convert, see, take first element as a pivot element and convert the second element is actually 0. So I need to make 4 and 3 as zeros. So R3 should be replaced as R3 minus 4 times R1, correct? And R4 should be replaced as R4 minus 3 times R1, right? This procedure we need to complete. So you'll get the answer to be 4, and you can work it out as a homework. Okay. If the question is not noted down, you can just take a screenshot. Okay. This one also we'll just discuss and move on to the theory part. This one you can try. Please try this question. Please try this question. Okay, so yeah, yeah, correct. All of you got the correct answer. So just commute under multiplication means if the two matrices commute under multiplication, that means A into B will be equal to B into A. So you just need to multiply this matrix with the second matrix and find the elements and compare it with BA. That will be equal to only if this particular condition is obeyed. That is if A is equal to B or if theta is equal to n pi. If you want, I can just quickly do it. Cos theta into C. I'll number this as A and B. So what will be AB? AB will be A times cos theta minus sin theta into 0 and cos theta minus sin theta into B. So this is minus B sin theta, A sin theta, then and B cos theta. So this is B cos theta. So this will be A into B. Now what is B into A? B into A will be A cos theta, sorry, A times, okay, A cos theta plus 0, okay, A cos theta. Now minus A sin theta. Now next is B sin B. What will be the other one? B sin theta here. B sin theta and B cos theta here. Okay. So this will be AB and this will be BA. Now if you compare, the diagonal elements will remain the same, right? The other diagonal, this is minus B sin theta and this is minus A sin theta. And this is A sin theta and this is B sin theta. So these elements will become same if A equal to B. Right? If A is equal to B, that elements will be same. Another point is there, that element will still be same if theta equal to n pi also. Because if theta equal to n pi, sin theta terms will all be 0. So it doesn't matter what is the value of A or B. If theta is equal to n pi, this terms will be 0. That is why we got the answer as A. Is it clear? Shall I proceed? Okay. I hope all of you got the answer. So I'm moving forward. So I have actually written down some more questions, but we'll discuss it in the last part. Can we reach the answer without working out? Okay. If the you can think about the answer without working out, because if A is equal to B, that becomes a scaled identity matrix, right? If A is equal to B, then I can say that matrix is A times 1 0 0 1. And identity matrix, if we pre-multiply or post-multiply with any matrix, the result will be same matrix. So I can guess the answer to be A equal to B. And also if theta equal to n pi, this becomes identity matrix, because or scaled value of identity matrix, because then these two terms cancel out. So naturally that will be a scaled identity matrix. So in these two cases, one of them turns out to be identity matrix. If and you know A into I is equal to I into A. Similarly, B into A, I equal to I into B. So if one of the matrix turns out to be identity matrix, naturally the multiplications will commute, right? So in that way you can conclude the answer to be A equal to B or theta equal to n pi, because under this condition this becomes a scaled identity matrix, or this becomes a scaled identity matrix. Okay, right. Okay, so other questions we'll discuss after the theory portion. Now we are left to work out one more thing. which is system of linear equations. Okay, we will discuss system of linear equations in detail today. System of linear equations. See, we can broadly classify the system of linear equations into two. One is the homogeneous class, homogeneous system of linear equations. Another is non-homogeneous system of linear equations. Okay. So you know what is meant by homogeneous and non-homogeneous now, because we have introduced the words homogeneous and non-homogeneous in previous classes. Homogeneous means the right side of the equation will be 0. So I can write AX equal to 0. The examples are, if I know x plus y equal to 0 and x minus y, or 2x minus y equal, sorry, x plus y equal to 0, right? Then 2x minus 2y equal to 0, minus x plus y equal to 0, and 2x minus 2y equal to 0. This is a homogeneous system of linear equation. Now we'll take an example for non-homogeneous case. Let us say x plus 2y equal to 5 and 2x minus y equal to 0. So this is a non-homogeneous case, because I have the equation of the form a times x is equal to a column vector b, right? Here, if you have a system of linear equations, the coefficient matrix A is, you just need to take the coefficients of the equation. First one is minus 1, 1. So minus 1, 1. Second one is 2, minus 2. Okay. Into x means the variable matrix. Here x and y are the variables. So x, y equal to column vector 0, 0. So this is an example of a homogeneous system of equations where A represents the coefficient matrix, X represents the variable vector, and 0 represents the resultant column vector. Similarly, here Ax equal to B, I can split the equation into coefficient and variable format. So the coefficients are here. What are the coefficients? 1, 2, then 2x minus 1. So 2 minus 1 times x, y will be equal to 5, 0. So this is an example of a non-homogeneous system of linear equations, because I have the format Ax equal to B, right? So in both these cases, what are the requirements for a system of linear equations to be consistent? Okay, we'll check for consistency first. Okay, how to check consistency? Then number of solutions. These are the things which you need to learn from a system of linear equations. Consistent means whether a solution exists or not. If a system of linear equation is said to be consistent, that means there is some solution for a that means then some solution will exist for that particular set of equation. And if the system of linear equation is inconsistent, that means there is no particular values of x or y, or the column vector variable vector xy, for which these equations are consistent or they are valid, right? So that is what is meant by consistency. Now our idea is to check for consistency. So we'll first consider the case of non-homogeneous system of linear equations, because we already know homogeneous system of linear equations are always consistent. Why homogeneous system of linear equations are always consistent? Because there is always a solution called as trivial solution. Okay, so you cannot say a homogeneous system of linear equations are inconsistent, because there is always a trivial solution, which is the variables, all variables 0 solution. Correct? Now we'll discuss the number of particular other solutions for a homogeneous case later. First, we'll discuss the non-homogeneous case of non-homogeneous class of system of linear equations in detail. Okay, so we'll take this particular example itself, which is okay. I'll take two different examples and see how they are actually giving the result. Okay, the first one is x plus 2y equal to 5. Another is 2x minus y equal to 0. So this is the first non-homogeneous system of linear equation. Another is x plus 2y equal to 5 and 2x minus y equal to 5. Right? Now I have the coefficient matrix here as 1, 2, 2 minus 2x minus y is 2x minus 1. Okay, 1, 2, 2 minus 1 into hy. I just write the coefficient matrix alone. Here the coefficient matrix is 1, 2. Okay, so both are same. 2 minus 1. Okay, in both cases coefficient matrix is same, right? Now to check for consistency, I will actually write one more column in addition to this coefficient matrix. That column I'll add from the resultant matrix, which is 5, 0. So what I have added here is, if the general format of the equation is AX equal to B, I have first written down the matrix A here. This is A. Now I have added the column B, correct? The column B. Now this matrix A column B is called as the augmented matrix. Okay, that is called as the augmented matrix. Okay, so here also I'll write that column. That column will be 5, 5, correct? So that is the augmented matrix. Now, if you consider the rank of this particular matrix, this is an augmented matrix. This is an augmented matrix for another system of linear equations. If you consider the rank of this particular matrix, what will be the rank of this matrix? Let us see what is going to be the rank of the matrix. How do you check the rank of a matrix? Actually, I can do the linear in elementary row transformation, because the first element is 1. So I'll take R2 into R2 changes to R2 minus 2 times R1, correct? That is the method. So I'll have the first elements remaining the same, 1, 2, 5. Second element 2 minus 2 will be 0. Minus 1 minus 4 will be minus 5. 0 minus, okay, 0 minus 2 times minus 10, right? Now you can see there is no further reduction possible. So this is already in the echelon form. Now I'll just again split back it into A and B. Now what is the rank of coefficient matrix? I can say the rank of coefficient matrix by considering the first part alone. Okay, this is giving you the rank of coefficient matrix. What is the rank of coefficient matrix? It is the number of non-zero rows. This row is a non-zero row. This row is a non-zero row. So it is 2. Okay. Now you check what is the rank of augmented matrix considering A as well as B. That will also be obtained from the same evaluation. The answer will be there are 2 non-zero rows. So the 2 non-zero rows means rank of coefficient matrix is also equal to 2. Okay. So rank of A and rank of A colon B. One is coefficient matrix, another is augmented matrix. So both are obtained to be 2 here. Now we'll see what happens here. Okay. The answer here will be, suppose I have 2 minus, so 1, 2, 5 here, 2 minus, so R2 changes to R2 minus 2 times R1. So that will be 0 here, minus 5 here, 5 minus 10 will be minus 5 here, right? So still you cannot any further reduce any further, which means there also the rank is going to be same. Now this is the condition required for any system of linear equation to be consistent. So that part should be clearly understood. The requirement of consistency. Okay, consistency requirement. Rank of A equal to rank of A colon B. You must read it as rank of coefficient matrix must be equal to rank of augmented matrix. That is the requirement. Okay, rank of coefficient matrix must be equal to rank of augmented matrix. That is the required condition for any system of homogeneous equations, non-homogeneous system of linear equations to be consistent. You need the rank of coefficient matrix and the rank of augmented matrix to be same. Is it clear? That is the first point you must not forget. The first point is, I'll write it down. I'll write down the first point. Rank of coefficient matrix, which is A, coefficient matrix A must be equal to rank of augmented matrix. Okay, what is augmented matrix? Augmented matrix is A colon B. If this condition is satisfied, then system of linear equations are consistent. That is the requirement for consistency. Now, what is the requirement for inconsistency? Naturally, if that is not equal, then inconsistent. If rank of A is not equal to rank of A colon B, then it is inconsistent. Or what does it mean? It do not have a solution. It do not have a solution. Okay. If the rank of A and rank of AB are different, that implies the system of linear equations are inconsistent and hence they do not have a solution. Right? Now, we can see two different cases of consistency and inconsistency. Let us see what it means geometrically. Suppose I take an equation of x plus 2y equal to, so that was the first question was, or I'll write a simpler example, x plus y equal to let us say 2 and x minus y equal to 0. I'll quickly check whether it is consistent. How to check? I'll write 1 1 2, then I'll write 1 minus 1 0, right? I'll check whether the rank is same, because I can easily say R2 changes to R2 minus R1, so that gives, see, this is actually AB, that gives 1 1 2, 1 minus 1 0, minus 1 minus 1 minus 2, 0 minus 2. So I have now two rows which are non-zero, which means rank of A is equal to rank of B. So rank equal to 2. Both ranks are 2. Coefficient matrix as well as augmented matrix both have a rank of 2. Now it implies the system of linear equation is consistent, and we have one more knowledge here. Since that rank is equal to the number of variables, here the rank is equal to the number of variables. Rank is equal to number of variables. What is the number of variables here? Number of variables is actually 2. 2 variables are there, right? If that rank is equal to number of variables, then the solution will be unique. If the rank is equal to number of variables, then there will be unique solution. Okay. So what are the three conditions which we have learned now? Rank of coefficient matrix equal to rank of augmented matrix is a must for any system of linear equations to be consistent. If it is consistent, it means there is a solution, right? Now we need to know how many solutions are there, whether only one particular solution is there, whether more than one solutions are there. To check that, you need to check the rank of the value of that rank. We can evaluate the rank using echelon form. If that is satisfying the first condition, that is rank of coefficient matrix equal to rank of augmented matrix, then we can conclude that the system of linear equations are consistent. But we still don't know whether it has got only one solution or more than one solution. For that, you need to check what is the number rank. Okay, what is the rank number here? The rank number is equal to, what is the rank number here? The rank number is equal to number of variables, which is equal to 2. Number of variables which is equal to 2. So okay, yeah, this is pretty simple. The points are very simple. So points are very simple. So it is number of variables. If the number of variables is equal to the rank of the matrix, if number of variables is equal to the rank of the matrix, then we can say there is only one particular solution for this particular case. And what does that pictorially means? Okay, what does that pictorially means? We'll see what does that pictorially means. I'll take two different examples and show you what it means. Okay, suppose I take the first example, which is x plus y equal to 0 and x minus y equal to sorry, x plus y equal to 2 and x minus y equal to 0. That is the first equation. And the second equation I am taking is x plus y equal to 2, second set of equations, and 3x plus 3y equal to 6. Okay, this is a pretty straightforward case. So we have seen 1, 1, 2, 1, minus 1, 0, and obtained the rank as 1, 1, 2. If I subtract this, this becomes 0, minus 2, minus 2, right? So here I have the rank is equal to 2, both augmented matrix and coefficient matrix. Coefficient matrix is this one, and augmented matrix is this one. Both ranks are 2, and that is equal to number of, this is A and this is A colon B, number of variables, right? That is equal to number of variables, which means I'll have unique solution. What it means pictorially, let us see what are the lines actually. Lines are x plus y equal to 2. If you plot the x plus y equal to 2 line, it will be like this. Okay, so it will be passing through 2, 0 point, and it will be passing through 0, 2 point. You can plot this x plus y equal to line, x plus y equal to 2 line pretty easily. Now what is this line x minus y equal to 0? X minus y equal to 0 will be a line in this direction, because y is equal to x is a straight line with slope equal to 1. You all know it is going to pass through origin also. Okay, now you can see it is intersecting only at one particular point. That is what is meant by unique solution. That is what is meant by unique solution. Okay, that happens if the rank of coefficient matrix and rank of augmented matrix are same, as well as that is equal to the number of variables. That will happen if and only if rank of coefficient matrix and rank of augmented matrix are same, as well as the number of variables. Okay, now let us consider this particular case. Here the equations are 1, 1, 2 and 3, 3, 6. Okay, so I have, this is the augmented part and this is the coefficient, sorry, this is a coefficient matrix and this is a column vector. Now if I convert R2 changes to R2 minus what is that, 3 times R1, I'll have 1, 1, 2, 0, 0, 0. Okay, so here you can see only rank is 1. If I take coefficient matrix as well as augmented matrix, both rank is equal to 1. So rank of coefficient matrix and rank of augmented matrices both are 1 here, but that is not equal to number of variables, correct? That is not equal to number of variables. So what can you say about consistency? Consistency is obeyed because rank of coefficient matrix and rank of augmented matrix are same, but that is not equal to number of variable, means it is not having a unique solution. We'll see how that picture will be. We'll see how that picture will be. If you plot the two lines, you can see x plus y equal to 2 is this particular line, and 3x plus 3y equal to 6 is a line which is lying on the same line. These two lines are effectively same, which means the two lines are meeting at each and every point, correct? So any point on this line is a solution for this particular problem, correct? If I have this particular problem, the solution is just x equal to 1 and y equal to 1, which is the meeting point of these two lines. Only x equal to 1 and y equal to 1. But this particular problem, every point on this line is a solution. See, this point, where it will be, this will be 2, 0, correct? See, 2, 0 will be a solution because I put x equal to 2, y equal to 0. So 6 here, x equal to 2, y equal to 0 is a solution. Similarly, 0, 2 will be a solution. Right, any point on this line will be a solution. That is why we call it will have infinite number of solutions. It will have infinite number of solutions. Now we'll see what is meant by inconsistency. Inconsistency happens if, suppose I have an equation 2x plus 3y equal to 10, right, and 4x plus 6y equal to 15. Now this equation, if I try to find the rank, 2, 3, 10, 4, 6, 15 will be there, right? Now I can change R2 changes to R2 minus 2 times R1, correct? So that will be 2, 3, 10. First row will not change. Second row will be 0, 4 minus 4, 0, 6 minus 6, 0, 15 minus 20 is minus 5. Now you can check the rank of coefficient matrix is 1 and rank of augmented matrix is 2. So 1 is not equal to 2. So system of linear equations are inconsistent. Inconsistent. So what is the condition? Rank of A not equal to rank of AB. One is called as coefficient matrix, another is called as augmented matrix. If that ranks are not equal, then it implies system of linear equations are inconsistent. What it actually means is you will have 2x plus 3y equal to 10 given by one line. Okay. Another line 4x plus 6y equal to 15 will be actually parallel to this line. If these two lines are parallel, they will never meet, which means there is no point on this plane where both the equations will be satisfied. They are not going to meet. That is the meaning of inconsistent set of linear equations. Okay, I'm back. Do you have any doubts? One more thing. Tomorrow and the day after tomorrow, can I take a? I mean, I'll be arranging a class. Is it possible for you to attend both days, Saturday and Sunday? Am I audible? Yes. Both days, okay, right? So yes, so I'll keep another class. Probability theory will be starting. Our sessions will continue after Sunday. Okay. Time will be this time itself is okay for all of you, or what about? Okay, we need not keep changing the time, right? We'll keep it this time itself. Okay, so 4:30 to 6 itself. Okay, your first probability class will be tomorrow. Second probability class will be day after tomorrow, and Monday I'll continue with Monday or Tuesday I'll continue with system. We'll have one more tutorial session for this linear algebra. Once we complete today's class, almost all the concepts will be covered. Rest, if something is missing, we'll be discussing all the branches gate questions. I have almost covered computer science and mechanical engineering. Now we'll discuss instrumentation, electrical, civil, and ECE. Okay, so that will be one more tutorial session. With that, I think most of the problems will be covered. Okay. Also, I'll be providing video solutions for some very important problems that for linear algebra that will be uploaded in YouTube as well. For other subjects, it will be available only for you through either Google Classroom or our app, which is to be ready at least by within 10 days. Okay. So I think for final years, S8 exam is going to start from July 1st onwards. I think the timetable is already out. KTU has published the timetable, right? So when onwards you need a break? I think we'll break from June. What is June? Let me see the calendar. Today is June 19. So 20, 21, 22, 23, 25. So June 25 onwards, I'll give a break for your exam, or June 24th onwards. So we'll take a class once the linear algebra second tutorial is over. We'll break there for 2 weeks, and then we will continue in full swing after your S8 exams get over. Maybe by July 8th it will be over. So July 10th onwards we'll restart the classes. Is that okay? Do you have your Viva, final course Viva or project evaluation, something pending? See, there are okay. There are a lot of students who have completed. Okay, all right. Okay, everything is over. So we'll restart right after your S8 exams. Correct? There is no need for any delay. Right after your S8 exams, we'll continue. From there onwards, from July 9th onwards, not over. For some colleges, it might not be over. Not over. Okay. Right. So you should you can communicate in our WhatsApp group if something is left out. Anyway, our time is 4:30 to 6. So normally your college timings is from 8:30 to 1:30, right? So it will not overlap. I hope we can restart after S8 exams. We can restart, and from then onwards we will have more classes. Okay, from July 8th or 9th onwards, we will have at least 5 to 6 classes per week. Okay. Okay, you can, okay, right. We'll have one problem worked out from this. Sir, what will be the solution if three lines in a space? Will that be the same as that for three lines in a plane? Not plane. Will that be the same as that for three lines in a plane? See, if three lines in a space, that is why it's very difficult to visualize your system of linear equations in a three-dimensional plane. Especially through the online platform, I cannot show you the vectors using any other thing, right? So it is easy to visualize in 2D geometry. In 3D geometry, actually, the same thing is getting extended to one more dimension. Okay, which means if two planes meet, that will give you a line of solutions. There will be actually infinite number of solutions. If that is, if you have, see, if you have a matrix of 3 by 3, okay, coefficient matrix 3 by 3, column vector added, so that will be 3 by 4 matrix. After this is A, this is AB, and if the rank of this are 2, okay, that implies there will be infinitely many number of solutions, because there will be a line of intersection of those two planes, correct? So if unique solution, that implies they'll meet only at one particular point, then that case rank will be actually 3 for both coefficient matrix and augmented matrix. If rank is same, and if that rank is equal to number of variables, then it implies it will have only one solution. Or if the rank is less than 3, it implies you will have infinitely many number of solutions. Actually, that is corresponding to what you have said. That is, two planes are meeting and one line will be, and the third plane is also passing through that line. So a single line will be full of solutions. That is what is happening in the three-dimensional case. Is it clear, Shane? Yes. Okay. So now we'll discuss the system of linear equations for homogeneous case. There you need to have some more idea. So homogeneous case I am discussing now. Homogeneous case. Homogeneous means you will have AX equal to 0, correct? Now we'll consider an example first. Suppose I have 2x plus 3y plus z equal to 0, x minus y plus 2z equal to 0, and 3x plus 2y plus 3z equal to 0. Okay, which means your system of linear equations could be written in the form A times, here x is a column vector given by x, y, z equal to 0, 0, 0, right? This is a homogeneous system of linear equations. I'll write 2, 3, 1, 1 minus 1, 2, 3, 2, 3. Okay. Now, we know one solution is there, which is called as the trivial solution. Trivial solution will always be there, which is x is equal to 0. We are not interested in the trivial solution. We'll say an independent set of solutions will exist if and only if the rank of A, if and only if the rank of A is less than the order of the matrix. Less than the order of the matrix. Okay. If order of the matrix is n, rank must be less than the order for any independent set of solutions. For example, in this particular case, n is equal to 3. And can you just evaluate the rank of this particular matrix? So you can always interchange rows and keep it whatever you want format, and then find the rank. Okay, what will be the rank of this particular matrix? I'll rearrange it as this. I'll make it as first row. So 1 minus 1, 2. Next is 2, 3, 1. Next is 3, 2, 3. So can you evaluate the rank of this particular matrix quickly? Rank of this particular matrix quickly? Yeah, Sujit, you are correct. Richard also correct. Answer is 2. I have actually kept the third row as a sum of first two rows. So R3 is actually equal to R1 plus R2, which means they are linearly dependent. So naturally this and R1 and R2 are linearly independent. So the rank is 2. So rank of this matrix is 2. which implies I have this condition satisfied, right? I have this condition satisfied. Now, how many set of solutions will be there? That depends upon the null space of this particular matrix. You know what is meant by the null space of a matrix? Null space of any matrix is the difference between the order and the rank of the matrix. Okay, null space of any matrix is the difference between the order and rank of the matrix. So I'll write what is null space of a matrix. Null space is equal to order of the matrix minus rank. Okay, if order and rank are same, null space is 0. Okay, which means if I have, suppose I have a 10 by 10 matrix and the rank is 7. What does actually that means? The order of the matrix is 10 by 10 and the rank is 7, means there will be 3 rows or 3 columns which are linearly dependent on all the other 7 rows or columns. I have 7 rows or columns which are linearly independent. 1, 2, 3, 4, 5, 6, 7 rows are linearly independent. The 8th row, 9th row and the 10th row, 8, 9, 10. They are linearly dependent on the first 7 rows. So I'll write like this. R1 is an independent row. R2 is an independent row. R3 is an independent row. R4, R5, R6 is an independent row. R7 also is an independent row. Now R8 I can write as R8. I'll write R6 plus R7. What does that mean? That means that this row is independent on first 2. I mean 6 and 7. Similarly, R9 if I write as R1 plus R2. That means that row is dependent on first and second. So rank 7 means there are 7 linearly independent rows and 3 rows are dependent. Now what is the null space? Null space is this number minus the rank. Okay, this number minus the rank. The order minus rank will always give the null space of a matrix. Now what is the importance of null space in homogeneous system of linear equations? Null space importance in homogeneous system of linear equations is because null space is important because we can say that many number of infinite set of solutions. One particular set of solution means, for example, if the in this particular case, the previous case, here the rank is actually equal to 2, correct? And the order is 3. So what is the null space here? Null space is actually 3 minus 2 equal to 1, correct? So I can say one set of infinite solutions is there. One set of solution. One set of solution means what? What do you mean by one set of solution? That means suppose I have one solution obtained for this particular equation as let us consider one solution. We don't know the solution. I have not calculated the solution. I have just written the matrix. So I am assuming the solution is x is equal to 1, y is equal to 2 and z equal to 3. If this is a solution, all the scaled values of this vector, this also solution means 1, 2, 3 is a solution. Okay, all the scaled values of this vector is also going to be a solution, which means I'll have 2, 4, 6, I'll have 3, 6, 9. All this will be a solution, but it will be considered as one set of solutions. That one set, that number is obtained by this null space. So what is the null space of the coefficient matrix? That many number of, what is the null space of the coefficient matrix? That many number of infinite, that many number of set of solutions will be there, which are linearly independent. Now I'll consider a case where the rank is actually equal to 1. Suppose I have the case where the order of the matrix is 3 and the rank is equal to 1. So what will be the null space? Null space will be n minus r equal to 3 minus 1 equal to 2. Correct? It implies there are two sets of linearly independent solutions. Two sets of linearly independent solutions are there. It means, suppose I assume one set to be 1, 2, 3 and another set to be 2, 1, 0. Okay. What does that mean? I know this is one set, which means all the scaled values of this set is also a solution, which means 1, 2, 3 is a solution, 2, 4, 6 is a solution, 3, 6, 9 is a solution, Like that it goes on. Okay. Similarly, this is another set of solution, which means I can say 420 is a solution, 630 is a solution, 8 what is that 840 is a solution. So that is also yes, sir, both are same. Which both are same means Sujit, what you meant by both are same? 123 or 120? So 123 or 120? 123. Okay, 123. This is 123. Okay. Yeah. This is one set of solution. Another is 210. Another set of solution. So, is the idea of homogeneous system of linear equations clear to you? If I ask you one particular question, see, my system of linear equations is given by Ax equal to 0, and I have the order of A to be 5 by 5, and the rank of the matrix is 5. How many solutions are there? If rank is equal to 5, how many solutions are there? Can you answer it? Ax equal to 0, A is a 5 by 5 matrix, and rank is equal to 5. It has got only one solution, which is unique and trivial solution. Unique and trivial solutions. Unique and trivial solution, which is 0, 0, 0. Right? Correct, correct. All of you understood what is trivial solution. Now, if I have the rank is equal to 4, how many solutions are there actually? How many solutions are there? Actually, there are infinite solutions. Right, Sujit, you are right. Actually, there are infinite solutions, but those infinite solutions will all lie on one particular line. Okay, those infinite solutions will all, for example, if I consider this particular point as a solution 2, 1, then this particular point 4, 2 will also be a solution. This particular point, all these particular points on the one set of infinite solutions will be there, and trivial solution will also be there. Now, if rank is 3, that means there will be two infinite set of solutions will be there. Two infinite set of solution. One line is this one, another line I can draw, another line I can draw in this particular direction. See, this will also be a set of solution. So, do you understand what is meant by set of solutions now? Origin is always a solution. Origin is always a solution. Now, this is what is meant by a set of solution. It need not pass through origin. Okay, you can have a line like this. That is also possible. This is a set of solution. So, this is the idea of system of homogeneous equations. This is the idea of system of homogeneous equations. Do you have any doubts regarding this? What we have taught today? Do you have any doubts? If you have any doubts, I'll discuss now, or I'll go to clear. Okay, is it clear? Right. The rotation matrix. Can you repeat it again? I'll repeat once more. No problems. So the system of homogeneous equations. The idea is, if you have the system of homogeneous equation, we can write it as Ax equal to 0. Naturally, there will be an order for A given by n, which means it will be an n by n matrix. Assume it to be an n by n matrix. Okay. Now we can always find, this is the order of the matrix. Okay. We can always find the rank of the matrix A. If the rank is marked as A, and if n is equal to R, that means n minus R equal to 0. So order and rank are same. We'll have only unique solution, which is the trivial solution. We'll have only unique solution, which is the trivial solution. Now, if n minus R is different, n minus R equal to 1, that means along with the trivial solution, you will have one set of solutions which are actually infinite in number, because the suppose the solution is 1, 1, 1, then you have 2, 2, 2 as a solution, 3, 3, 3 as a solution, 4, 4, 4 is a solution. No problem, right? So all those are solutions. Right? Do you want an example for this particular problem? I'll just give an example. Okay. I'll take an example. Let us say x plus y minus 2 equal to 0. Sorry, minus z equal to 0. X plus y minus z equal to 0. Another is 3x plus 5y. Okay. Minus 4z equal to 0. Right? Next is 2x plus 4y minus 3z equal to 0. Okay, this is one particular example of a system of homogeneous linear homogeneous equations where I have the a coefficient matrix given by 1 1 minus 1 3 5 minus 4 and 2 4 minus 3. Now you know the order of this matrix is n is equal to 3. Can you quickly say what is the rank of this particular matrix? Can you quickly say what is the rank of the particular matrix? So okay, rank of the matrix is 2. Okay, rank of the matrix is 2. Right, rank of the matrix is 2. Right, easily you can evaluate. For those who cannot quickly do it, you can always screenshot the slide and work out later, or the recorded version will be available at least by tomorrow noon time, so you can watch it and work it out. Okay, so the rank is equal to 2 means I will have actually n is equal to 3 and r is equal to 2, so n minus r is actually equal to 1, right? N minus r is actually equal to 1, which means I'll have one set of linearly independent solutions. Since this equation I have mentally calculated the solution to be 1 1 2, this should be a solution. 1 1 2, let us see 1 1 2 is a solution or not. X is equal to 1, y is equal to 1 and z is equal to 2. So if I put 1 1 2, 1 plus 1 minus 2 equal to 0, 3 plus 5 8 minus 8 equal to 0, 2 plus 4 6 minus 6 is equal to 0. Now, what I meant by infinite set, if I have just one solution, that implies any scaled value of this number is also a solution. Any scaled value of this number, this set, that is 2 to 4 will also be a solution. You check 2 to 4, 2 plus 2 minus 4, correct? 3 into 2, 6, 5 into 2, 10, 16 minus 4 into 4, 0. 2 into 2, 4, 4 into 2, 8 plus 4, 12, minus 3 into 4. That is also a solution. This is also a solution, right? If you take 3, 3, 6, that will also be a solution. This is what is meant by one set of infinite solutions. One linearly independent set of, this is one linearly independent solution. Now, if the rank happened to be 1, for some other question, if the rank happened to be 1 and n happened to be 3, then n minus r equal to 2. That implies along with one set of this solution, another linearly independent, for example, 0 1 2, 0 1 0, okay, 0 1 0. Then 0 2 0 will be a solution, 0 3 0 will be a solution, 0 4 0 will be a solution, etc. Is the idea of system of linear equations for both homogeneous and non-homogeneous clear to you? Let's see, it is clear to you. Okay. Number of linearly independent solution is same as nullity. Yeah, that is what I have mentioned, right? Nullity or null space are same. That is what is meant by nullity. Nullity or null space is both are same. Number of linearly independent solutions is actually nullity or null space, right? So actually we have come to the end of our linear algebra theory session. One more point I forgot to tell you regarding the eigenvector, because when I discussed today's first problem, shall I proceed with this now? Is it okay with all of you? Are clear with system of linear equations, homogeneous and non-homogeneous? I'll just briefly split it into two. One is homogeneous, another is non-homogeneous. I'll just this slide will be useful for you. Okay. Another is non-homogeneous. How many solutions for homogeneous and non-homogeneous? So 3 by 3. How many solutions for homogeneous and non-homogeneous? I did not understand what you are writing.
Sir, if the matrix is 3 by 3 matrix,
yeah.
Okay, so if it is a homogeneous, so it is A matrix is 3 by 3 matrix. So if it is a homogeneous equation, then how many solutions are possible? Similarly, if it is a non-homogeneous, how many solutions are possible?
If the matrix is 3 by 3.
Yes, sir.
Yeah.
Okay, if it is a, it comes under a homogeneous category, how many solutions are possible? Similarly, if it is coming under non-homogeneous, how many solutions are possible?
Okay, I think that is what we have been discussing today. The question is for homogeneous, if the homogeneous case is Ax equal to 0, I'll write it down. You can just read it from this particular thing. Okay,
Okay, sir.
Ax equal to 0. This is Ax equal to b. Okay, now if the order, I am assuming the order of both as n by n here, n by n here also. Okay, and the number of variables, I am assuming it to be okay, here the rank is number of variables is assumed to be, let us say, k. Okay, now if this is an n by n matrix and the rank, this is the order and rank is r. Okay, if n equal to r, then only trivial solution. If n equal to r, then only trivial solution. Okay, otherwise if n is less than r, sorry, if r is less than n, then n minus r set of linearly independent solutions will be there. Then there will be n minus r set of linearly independent solutions will be there. Each set will have infinite number. That is what I have explained. Each set will have infinite number of solutions. Then there will be, if rank is less than n, then there will be n minus r set of linearly independent solutions will be there. This is what is about homogeneous case. Now the non-homogeneous case, this will be consistent. Here there is no issue of consistency because it is always going to be consistent in the case of homogeneous. But non-homogeneous, if it is consistent, if and only if rank of A is equal to rank of A colon B. Rank of augmented matrix and rank of coefficient matrix are same. Now, if consistent, then if the rank, if consistent and if it is consistent only, then it will have solution. If that rank is equal to number of variables, let us call number of variables here as r, or let us say number of variables is x. Let us say x. If the number of rank is equal to number of variables, okay, if the number of variables and rank are same, then it will have only unique solution. It will have only unique solution. Okay, if the rank is less than number of variables, if the rank is less than number of variables, then there will be then infinite number of solutions. Infinite number of solutions. So this is what is it in a nutshell. This slide will should give you all information regarding whatever we have taught in the last 1 hour. So actually it is it is down to a single page. This information is enough for you to solve any gate question. I hope it is clear to you. I actually don't want to miss one point which I forgot to tell you when I did the problem in the first problem which I did. I think I missed that point. Okay. No more questions, right? How many solutions? Yeah. I hope you can take. You want time to take down this note, this slide? Have you all taken this down? This is a very important page. This page should give you complete picture about a homogeneous as well as non-homogeneous system of linear equations. This is enough. You must actually understand the concept rather than trying to by heart what say, or the whole of linear algebra course I have been trying to make you understand more and more concepts rather than by hearting the tips or equations. Actually, gate problem solutions you can do in many different ways, but we were trying to do it more conceptual way. Right. Okay. So I'm moving to one more point which I missed during the first problem which we took. I think I can take back that problem. Okay. This was the problem. Yeah. This problem, do you remember? I have the matrix which is, I'll rub off everything. Okay. So this was a question where we have learned a new thing, that if any row or any column is having only one non-zero element, then that particular element, if it happened to be on the diagonal of the matrix, then that value will be an eigenvalue. That is what I have told you, right? I'll give another example for this particular problem. Suppose I have a matrix like I'll give you one question: 2 4 3 0 7 0 0 0 sorry, okay, okay, 8, let this be 8 802 802. This is 8. Okay, can you say what is an eigenvalue of this matrix? Quickly, can you say what is an eigenvalue of this matrix? Yeah, 7. It is 7. This is simply what we have learned in the first 5 minutes of this class. Okay, it is 7 because you have one particular column. Remember the term column. Okay, I'm telling you column. One particular column with only one non-zero value, and that value is in the diagonal of the matrix. Then that particular value will be an eigenvalue. And my next point is the corresponding eigenvector will be actually the position. You check the position of this 7. It is the second position, right? You put only 1 in that particular position. This will be an eigenvector corresponding to this particular eigenvalue. That is what I missed when I discussed this problem. That is an additional concept. Okay, you see 208 470, okay, 470 and 302. If I multiply that with 010, what will be my result? 2 into 0, 0 into 1, 8 into 0. So the result is 0 here. 4 into 0, 7 into 1, 0 into 7, 0 into 0. So 7 here. 3 into 0, 0 into 1, 2 into 0. So 0. So what is the answer actually? Answer is actually 7 times 0, 1, 0. Correct. So that eigenvalue is corresponding to this particular eigenvector. Right? This particular eigenvector. Now may I ask you one question? What will be the eigenvector corresponding to the eigenvalue 4 here? What will be the eigenvector corresponding to the eigenvalue 4? Can you quickly say what will be the eigenvector? Yeah, Manjunath. Yeah, it will be
0 0 0
0
1.
0. Yeah, very good. All of you are giving correct answers. I'm very happy that you are quickly catching the ideas now. So in general, our theory sessions are over. I actually don't know if I have missed out some points. We'll see a lot more problems. If I have missed some points, I'll discuss them. I hope if all of you have attended all the theory sessions, naturally your knowledge level in linear algebra must have improved by now. Okay,